Hi guys, this is Physics 212 Charge Tape Lab, the second one. Introduction, purpose, plus preview of main results. Build on the findings from Lab 1 by developing a more advanced computer model to develop the electrical force and charge present on the charge tape. Represent the tape as a line of charges rather than a single point charge to reflect the distribution of charges along its length. Key findings: the charge magnitude on the piece of tape is calculated to be 2.49858 times 10 to the negative 8 coulombs. This value is twice as the charge estimated using the point charge model in Lab 1. Introduction, models plus assumptions. The experimental model used in the was the same as in lab one. The computation model represent the tape as a line charge uh to calculate the electrical force and charge. The assumptions are air resistance was disregarded. Each a U tape carries an identical charge. The charge is uniformly distributed along the length of the tape. Fundamental principles. We have Coulomb's law slash electrical force, which is Fe equals K Q1 times Q2 over R squared. We have electrical field of the distributed charge, E net equals sigma IE, EI, gravitational force, F equals ma, mass times gravity, and Newton's second law, F net equals delta P over delta T. Experimental model. Parameters. Charged U tapes. The surroundings, everything else, including the base tapes, supporting the environment. Initial conditions. The electrical charge is initially 0, 0, 0. Process. Two pieces of U tape labeled tape A and tape E were quickly created by charging peeling tape from the base and inducing a charge on the U tape. Tape A was identified as positively charged because it attracted to a negatively charged pen. Tape B was suspended by its own ends using two rulers. When tape A was brought near, tape B levitated due to the repulsion of positive charges. The distance between tape A and tape B was recorded. Experimental data plus lab 1 results. Physical properties of U-tape. 8.5 inches. Mass was 0.00215 kilograms. The width was 0.019 meters. The distance between the tapes were 2.2 centimeters or 0.02 meters if we convert that. And the results from lab 1 were the magnitude of the electrical slash gravitational force acting on the tape was 2.11582 times 10 to the negative 3 newtons. The magnitude of the charge on one piece of tape was 1.0667 times 10 to the negative 8 coulombs. Here's our computational model that we use to code how it reacts on the next page. Here's our model. The white arrow is the electrical force. Tape B is the force acted on uh the tape. Tape A is the blue line, and then the gravitational force is the yellow arrow. And as you can see, our computations are down below. Discussion. Discrepancies between model and experiment. In real-life scenarios, gravitational force and electrical force are not perfectly balanced, and additional forces likely act on the charge tape. Dividing the tape into smaller pigments of point charges improve the accuracy of the computational model compared to treating the tape as a single point charge. Sources of error. Variation in charge between different pieces of tape, mishandling the tape, potentially causing the charge inconsistencies, exclusion of other environmental forces such as air resistance from the model. What if? You model each piece of tape as a single point charge as experiment in the previous lab. Compare the estimated charge values derived from the experimental data using a point charge model to obtain a line charge model. Lab 1 charge estimate 1.667 times 10 to the negative 8 coulombs. Lab 2 charge estimate 2.49858 times 10 to the negative 8 coulombs. Why? Do these differ? And which of the following is more likely to an actual charge? Provide the reason to support your conclusion. Conclusion. Dividing the tape into smaller segments modeled as the electrical charges provided a more accurate method of calculating charges. Breaking the tape into infinitely small segments to compute the electrical force would yield even greater accuracy. Point charge models are insignificant for accurately representing the charge distribution of larger macro scale objects. That's the end of my PowerPoint. Thank you for listening.